Welcome back to the deep dive. Today, we're looking at something special. It's not just a system, it's really the foundational document that dictates the very viability of next-generation flight.
It really is.
We've been given access to what you can only describe as a strategic blueprint. It's an engineering specification from a senior aerospace propulsion architect, someone specializing in the P-13 series parallel hybrid eVTOL architecture.
And that's the key thing to understand right from the start. This is not just a manual. It's not a list of parts. It's a top-down, systems-level strategy.
That's strategy.
Yes. The architect here has used a classic, really rigorous approach. It's what you'd call MEC, mutually exclusive, collectively exhaustive.
Right, the McKinsey framework. Break it all down.
Exactly. To break down one of the single greatest engineering obstacles in urban air mobility, heat. And their mission, which is now our mission for this deep dive, is to really get inside how engineers solve a physics problem that frankly determines whether these aircraft are safe, reliable, and ultimately profitable.
That's the core goal. To understand that evolution, how do you move beyond just, cooling a component to creating what the source material calls, again and again, a performance enabler?
It's a fundamental shift in thinking.
Right. This integrated thermal management system, or ITMS, it's basically the nervous system of this P-13 aircraft. It dictates everything from its maximum takeoff weight to whether it can even operate reliably on a hot summer day.
And if you need any proof of just how high the stakes are, you just have to look at the numbers. The financial forecast the architects themselves use to justify this level of engineering. It's staggering.
What are we talking about?
The global market for eVTOL thermal management. It's projected to grow from an already huge $14.1 billion this year, 2024,
Okay.
to a massive $51.1 billion by 2032.
Wow.
That's a compound annual growth rate of 17.38%. And that tells you one thing, and one thing only. Managing heat isn't some secondary design problem. It is the fundamental technological bottleneck that once you solve it, you unlock this entire industry.
So let's unpack that. Let's get into this high-stakes environment. The P-13 is a series parallel hybrid. So that means we have, traditional combustion power.
A thermal propulsion unit, or TPU, an internal combustion engine.
Right, an ICE. And it's working right alongside these incredibly powerful high-voltage battery systems. So what specific, really unique thermal challenges does this Frankenstein's monster of propulsion create that a traditional jet or even a pure EV doesn't have to deal with?
Well, it creates what the architects in the spec literally call the thermodynamic crucible. And the foundational problem is what they term the dual heat source dilemma.
The dual heat source dilemma.
We've been calling it the fire and ice problem, because you have two utterly incompatible temperature requirements operating at the same time inside a very, very compact airframe.
Okay, let's start with the fire. That's the high temperature side, I assume.
That's the ICE, the TPU and its turbochargers. These systems are designed to run hot. They reject heat at really high temperatures, typically operating in the range of 90 to 110 degrees Celsius.
So you need a dedicated, really heavy-duty cooling system just for that component.
Absolutely. That's your traditional brute force thermal load, the kind of thing automotive engineers have dealt with for a century.
But then you have the ice side.
And that is the high voltage energy storage system, the ESS, the battery. And for lithium-ion chemistries, thermal management isn't just about performance anymore. It's about survival.
Right.
The battery has to be kept rigidly inside an extremely narrow and sensitive temperature range. We're talking 25 to 45 degrees Celsius.
25 to 45, that is a tiny window.
It is. If you push it above 45 C for any real length of time, you start accelerating chemical degradation. You're literally killing the battery's lifespan, and you start introducing serious safety risks.
So the architect has to, guarantee that the 100-degree heat from the engine never, ever touches the 45-degree ceiling on the battery.
Under any circumstances. In any flight phase, that's the job. You have a 65-degree temperature differential that has to be managed at the same time, often with shared airflow paths. It's a huge challenge.
That's challenge one. But you mentioned another, and it seems a little counterintuitive. The low-grade waste heat problem. If electric parts are so efficient, why is it so hard to cool them?
It does sound like a paradox, doesn't it?
Yeah.
But it's just pure physics. The electric components, your batteries, your inverters, your motors, they are incredibly efficient.
Right. They turn most of the energy into motion, not heat.
Exactly. But the heat they do generate is what physicists call low grade. And the efficiency of any cooling system is fundamentally dependent on the temperature difference, the delta T between the thing you're trying to cool and the air around it.
Ah, okay. So because the electric parts need to run cool anyway, there isn't a big temperature gap between them and the outside air.
Precisely. Let's say your very fancy, very efficient silicon carbide inverter needs to stay below, I don't know, 80 degrees Celsius. And you're flying on a hot day, maybe the ambient air is 40 degrees C.
Your delta T is only 40 degrees.
It's only 40 degrees. And that small difference severely limits the natural rate that heat can dissipate. You can't rely on some huge scorching temperature gradient to just naturally push the heat out like you could with a jet engine turbine.
So you're fighting the laws of thermodynamics.
You're forcing low-grade heat rejection. And that demands very precise, very high surface area and very powerful active cooling solutions. It puts a ton of pressure on the hardware.
And that leads right into the third big challenge, which, from a strategic point of view, might be the most critical one, the extreme mission profile.
Yeah.
When is this whole system under the most stress?
It's doing the most critical phases of flight, vertical takeoff and hover.
Right at the beginning.
The specs show that during this period, the heat generation rate from the entire system engine and battery working together spikes to about 3 times the rate you see during the long, easy cruise phase.
And this peak load, how long does it last?
It's a critical window. It can be anywhere from 30 seconds up to 120 seconds. 2 full minutes of peak thermal load.
So the whole propulsion system is at max power. You're drawing insane current from the battery. You're spinning the turbine at max RPM.
Exactly. But now think about the state of the aircraft during that 2-minute thermal sprint. It's hovering.
Its forward airspeed is 0, or close to it.
It's near 0, which completely negates the primary cooling mechanism of pretty much all of high-speed aviation. Ram air cooling.
Right, forcing air through the radiators with forward motion.
That system, which does 90% of the work in cruise, simply vanishes. It's gone. At the exact moment, the thermal stress is at its absolute peak.
So the ITMS has to do all the work on its own.
It has to rely entirely on its active components. Powerful fans, pumps, specialized cold plates. It has to survive that moment all by itself.
That's the architect's dilemma right there. You have to build a system that can isolate fire from ice, struggle to push out low-grade heat, and then do its hardest work precisely when its main passive cooling source has completely failed.
It's an incredible challenge, and it requires a completely integrated, strategic architectural solution. Which brings us to how they actually solved it. The tri-loop topology.
The tri-loop topology.
It is. This is where that MECE thinking really pays off. The architect knew that trying to manage 3 wildly different temperature requirements and safety standards in a single fluid loop was, well, it was structurally impossible.
So you isolate.
You physically and strategically isolate. You break the system down into 3 independent, physically separate thermal loops.
Okay, let's define these 3 mutually exclusive loops and what they do.
Loop A is the high temp loop, or HTL. Its only job is to focus on the fire side. So the thermal propulsion unit, the ICE, and the super hot air coming out of the turbocharger intercooler.
And its temperature range.
It's high. We're talking in the 85 to 110 degrees Celsius range. And the mandatory fluid here is a standard 50-50 ethylene glycol water solution, EGW.
Okay, EGW, that's basically standard antifreeze. It's robust, it's great at carrying heat. Why is it the right choice here?
Well, it has a very high specific heat capacity, which just means it can absorb a massive amount of heat energy per unit of volume. Plus, its antifreeze properties are, completely non-negotiable for high-altitude flight and the cold weather certifications the aircraft needs to get.
Right, for global airworthiness. So that's the hot loop. Now, moving to the electric side, the 800-volt system, which is split into 2 separate loops for precision.
Correct. Loop B is the mid-temp loop, or MTL. This loop's job is to handle the really hot power electronics. This means the high heat flux, 6 silicon carbide inverters for the P1 and P3 motors.
The brains of the electric drive.
The brains and the muscle. It also cools the motors themselves and the DC-DC converters. The temperature is lower than the HTL, but it's still pretty high for electronics. You're generally targeting 40 to 65 degrees Celsius, though some of the newer Sukkerthy components can, momentarily tolerate up to 85 C.
And then there's Loop C, the most sensitive one of all.
That's Loop C, the low temp loop, or LTL. This is 100% dedicated to the energy storage system, the battery.
And its tiny temperature band.
Its narrow, non-negotiable temperature band of 25 to 45 degrees Celsius. This is the component that requires the absolute most stringent thermal uniformity and precision control.
So we have three loops, all running at wildly different temperatures, but the mid-temp and low-temp loops, they share a critical common feature, the fluid itself. And this seems to be the heart of the dual fluid strategy.
This is the pivotal strategic decision in the whole document. And it's driven entirely by safety and regulatory compliance. Both the MTL Loop B and the LTL Loop C must use a dielectric fluid, specifically polyalpha-alphan or PAO.
PAO.
This is the absolute foundation of the high-voltage safety architecture.
So why is that non-negotiable? I mean, why can't they just use the cheaper, more common EGW, which we just said is thermally excellent?
Because EGW is conductive. It conducts electricity. The P13 operates on an 800-volt high-voltage bus. If a pipe-carrying conductive EGW were to rupture or just leak onto that bus bar, you would have an immediate guaranteed electrical short circuit. You'd have massive arcing and likely a rapid thermal event, a fire that would lead to a catastrophic failure.
But PAO is non-conductive.
It's an electrical insulator. It's a dielectric fluid. If it leaks, it just makes a mess. It doesn't cause a short circuit.
So the choice of PAO fundamentally eliminates the risk of the coolant itself causing an electrical fire.
Exactly. The specification demands absolute compliance with a standard called SAE ARR 6127 for high-voltage safety. And to meet that, the PAO has to have a breakdown voltage. That's its ability to resist an electrical current of greater than 25 kilovolts per 2.5 millimeters.
That's an incredible amount of electrical resistance.
It's massive. And it ensures that even if the fluid completely saturates the high-voltage components, safety is maintained. This decision just shows you the architect's priorities. You achieve safety and certification first, and only then do you optimize for performance.
That level of safety isolation it's really compelling. You've got physical separation of the thermal needs with the tri-loop and a chemical separation of risk with the dual fluid strategy.
That's the MACE approach in action.
Right. But a blueprint is useless without measurable goals. So let's shift to the mandatory functions, the FUNC TMS, and the non-negotiable quantitative KPIs that really define the system's performance redline.
These 5 functions, they're essentially the contractual obligations that the system has to fulfill. They go way beyond just simple heat rejection, and they integrate the thermal system right into the aircraft's core mission profile.
Okay, let's start with the most immediate challenge. FUNC TMS-01, peak load rejection.
This is that moment of truth we talked about. That 90-second vertical takeoff sprint at maximum takeoff weight, or MTOW. This is when the system has to prove its cooling muscle.
And the mandate is clear.
Crystal clear. The CFEC inverter junction temperature, that's the hottest, most critical point in the power electronics, must stay below 150 degrees Celsius. And the battery cell temperature, which is long-term risk, has to stay below 55 degrees Celsius.
So why is 150C the red line for the inverter? What happens if it goes over?
If you exceed that temperature, even for a moment, you get a sharp drop in the semiconductor's efficiency. You can cause permanent degradation or even immediate functional failure. The entire power delivery chain, the very ability to generate lift, relies on holding that 150C ceiling for the full 90 seconds.
If it fails, the system has to cut power.
It has to D8 power, which is completely unacceptable during takeoff.
Okay, so then we tackle the complete opposite extreme with FUNC TMS-02, which is battery preconditioning.
This one is all about operational utility, commercial viability. If your aircraft is sitting on the tarmac in, say, a minus 20 degrees Celsius environment, the battery can't perform its mission. It's too cold.
Right. It can't deliver full power and it can't fast charge.
Exactly. So the system has to be able to actively heat the battery. It can use waste heat from the ICE or dedicated electric heaters, but it has to bring the temperature up to above 10 degrees Celsius within a mandated 20 minutes.
20 minutes.
If that preconditioning takes an hour, the aircraft is commercially useless for the kind of rapid turnaround missions it's designed for.
Okay, that makes sense. Then FUNC TMS-03, after-run cooling. This seems like a critical reliability feature, but for the engine side.
It is. It addresses a silent killer. Heat soak back.
Heat soak back.
When you shut down the ICE after a mission, all that residual heat, especially around the really hot turbine components, it starts to soak back into the cooler areas. And the most vulnerable parts are the incredibly precise turbocharger bearings.
And that heat can damage them.
It can coke the lubricating oil. It basically solidifies it, which leads to bearing failure the next time the engine starts. So to prevent that, auxiliary electric pumps have to automatically kick on for 5–10 minutes after the engine is off, just to circulate fluid and prevent that localized thermal damage.
Smart. Okay, now moving from reliability to pure efficiency. FUNC TMS-04 drag management. This is where the thermal system really becomes an active performance component, not just a cooler.
This is a classic aerospace optimization problem, those external radiators that you need for heat rejection. They create a huge amount of aerodynamic drag.
Which eats into your range.
It severely eats into the eVTOL's precious range.
Right.
So the specification mandates a dynamic solution, actively adjusting radiator cowl flaps. They're basically louvered vents that open and close based on the real-time thermal need.
And the target is aggressive.
Extremely aggressive. In pure electric cruise mode, when cooling needs are minimal, the system has to be able to reduce that cooling drag by over 60% compared to just having the flaps stuck fully open.
A 60% drag reduction is a massive performance gain. That must demand incredibly precise control of those physical vents while the aircraft is flying.
Oh, absolutely. The flight control computer is in a constant balancing act. It's weighing the thermal margin against the aerodynamic penalty second by second. Every tiny bit of drag you reduce translates directly into more range and lower operating costs.
And finally, FUNC TMS-05. Waste heat recovery. This is about turning a thermal liability into a functional asset.
Exactly. In cold weather or at high altitude, the system has to be smart enough to capture the high-grade waste heat from the icy heat that you would normally just dump overboard through the radiator and repurpose it.
Where does it go?
It gets routed to the Cabin Environmental Control System, the ECS, for heating, or potentially for wing de-icing. And the architect makes a key point here. This integration saves up to 15% of the valuable battery energy that would otherwise have been used just to run electric heating elements.
So those 5 functions, they set the operational boundaries. Now let's get into the hard numbers. The quantifiable acceptance KPIs. The metrics that, if the system fails them, lead to a total rejection of the design.
The KPIs of the contract, they're non-negotiable. First up, thermal uniformity. For the battery, its chemical life is dictated by the hottest single cell. So to maximize its lifespan and prevent localized stress, the internal temperature difference within any single battery module has to be tightly controlled.
How tight?
Less than or equal to plus or minus 3 degrees Celsius. That level of precision requires incredibly sophisticated multi-zone cooling management.
And then there's the robustness check, no derating capability.
This is the system's guarantee of power. It has to sustain that full power hover for 90 seconds, even when it's operating in extreme ambient heat. The spec defines that as ISA plus 35 degrees Celsius.
The hottest day on the hottest runway.
That's the test case. If the system has to throttle back or reduce power output because it can't reject heat fast enough in that environment, the design is rejected, period.
The third KPI focuses on the thermal system's own efficiency parasitic power consumption.
Right. You have to account for the fact that the pumps, the fans, the controllers, they all consume energy themselves. And that energy eats into the aircraft's usable range.
So you have to cap that.
You do. The total thermal system consumption has to be minimal. Ideally, below 3% of the total output power during the cruise phase, though some sources in the spec allow up to 5%. But the difference between 3 and 5% can be the difference between making your required route distance or falling short. It forces engineers to use high-efficiency components everywhere.
Then we come back to high-voltage safety with insulation resistance.
This is a critical electrical health check for those 800-volt dielectric loops. The HV circuits have to maintain an insulation resistance to ground of greater than or equal to 2 megaohms and greater than or equal to 500 ohms per volt.
And this is a continuous check.
It is. It's a constant monitor to make sure the PAO fluid hasn't degraded, hasn't picked up contaminants, and all the physical insulation is still intact. It's a prerequisite for flight safety, especially at altitude.
And finally, the ultimate aerospace metric, specific cooling power.
Weight is the enemy of anything that flies. This KPI measures the cooling capacity relative to the system's own mass. The cooling capacity has to be robust, greater than or equal to 2.5 kilowatts of heat rejection per kilogram of system weight.
Which forces engineers to lightweight everything.
Constantly. They're forced to use titanium, microtube aluminum, complex 3D printed structures. Anything to maximize the cooling power they get for every single ounce of weight they have to carry.
I really appreciate how these KPIs translate abstract physics into concrete performance guarantees for the pilot and the operator. We've set the targets. Now we need to see the hardware. How does the architect specify the cutting-edge tech needed to actually hit these radical KPIs in each of those dedicated loops?
Right, so we're moving from the strategic what to the engineering how. And the focus is all on component selection, guided by maximum thermal efficiency and critically redundancy.
Let's start with the high temp loop, the HTL, the ICE side.
The HTL requires what you could call blended reliability. The primary cooling pump has to be engine-driven, it's mechanical, to ensure its inherent reliability anytime the engine is running. That's your foundation.
But it's complemented by something else.
It is, by a separate, dedicated electric auxiliary pump. And that auxiliary pump is the one responsible for that critical FUNC TMS03, the after-run cooling function we talked about, to prevent heat soak back. You absolutely need both to achieve full reliability.
And the heat rejection path itself, the radiators.
Integration is the key word here, all to save drag. The HTL heat exchangers have to be physically integrated, either stacked right next to, or in a serial air path with, the med-temp loop exchangers.
So they share the same airflow.
By sharing the same external airflow path, you minimize the number of air inlets and outlets you need. And that is a massive win for aerodynamic efficiency and for weight reduction.
Okay, now to the med temp loop, the MTL, the 800-volt power electronics. This is where the technology seems to jump, several generations past standard automotive stuff. Let's start with motor cooling.
Standard jacket cooling, where you just fluid around the outside of the motor casing, it just can't handle the heat generated by these high-performance, high-RPM electric motors, especially not during takeoff.
So what's the mandate?
The specification mandates direct oil cooling. The dielectric PAO fluid has to be sprayed directly onto the motor winding ends.
Inside the motor.
Right inside, through specialized nozzles, or even routed through a hollow shaft in the motor. This direct contact with the internal heat source drastically shortens the thermal path and boosts cooling efficiency by up to 50%.
So instead of cooling the shell of the motor, you're cooling the copper conductors themselves, right where the heat is actually being generated.
Precisely. And that same intense heat flux density applies to the CC power modules in the inverter. They generate a ton of heat in a tiny, tiny area. To manage that density, the cold plates they're mounted on must use 3D printed microchannel structures.
Okay, why 3D printing? Can't a standard machine-milled cold plate work?
A standard cold plate is stamped or milled, and that really limits its internal complexity. 3D printing lets engineers create these incredibly intricate, complex internal microchannel geometries.
What do they look like?
They look almost like miniature coral reefs inside the metal. And that structure maximizes the surface area for heat exchange in the smallest possible volume. This kind of advanced manufacturing is absolutely essential to meet that cooling capacity KPI in the constrained space of an airframe.
And because the MTL is what powers the thrust, its pumps have to have maximum redundancy.
It's mandatory. Dual redundant 800-volt electric pumps. And the requirement isn't just that a second pump exists. The specification is connotative. It says that if one pump fails, the surviving pump must provide at least 60% of the nominal flow rate.
Why 60% specifically?
That 60% is the critical flow rate threshold that the system safety engineers determined. It's the absolute minimum required to ensure the motors and inverters stay just cool enough for the vehicle control unit, the VCU, to command a safe power DA rating and enable that continued safe flight and landing mode.
CSFL. So you won't have full power, but you won't crash either.
That's the idea.
Okay, here's where the engineering gets really, really insightful for me. The low temp loop, the LTL, for the batteries. We know they're using high-density 21700 cylindrical cells. So how on earth do you cool those things during those extreme 10C to 30C discharge rates in vertical flight?
This is maybe the most elegant solution in the whole specification. It's called tab cooling. The architects recognized that traditional cylindrical cell cooling, where you just flow fluid along the side of the cells is a huge thermal bottleneck.
Why?
Because the heat generated by electrical resistance is highest where the current actually enters and exits the cell at the positive and negative tabs.
So instead of cooling the periphery, the outside, they target the origin of the heat.
Exactly. The cold plate makes direct thermal contact with the copper and aluminum tabs on the ends of the cells, which effectively short-circuits the thermal path. This dramatically reduces the thermal resistance by over 50% compared to traditional jacket or side cooling.
And that's how they hit that crazy plus or minus 3-degree uniformity KPI.
That's how. It's the only way to ensure that longevity and maximum power delivery when it's needed most.
And to handle those instantaneous heat spikes during the 90-second takeoff, they have a clever thermal buffer solution.
That's the optional but highly recommended integration of phase change materials. thermal buffering, or PCM.
PCM, how does that work?
Think of PCM. It could be a specialized paraffin wax or polymer compound as a thermal sponge. It's integrated right into the cold plate structure. It doesn't actively remove heat, but when a sudden heat spike occurs during takeoff, the PCM absorbs that transient energy through what's called the latent heat of fusion.
Melts.
It changes phase, it melts without its own temperature rising significantly. It shaves the peak of the thermal load.
So it absorbs that immediate sharp spike.
It does. And what that allows is for the main continuous duty external radiator, which is heavy, and causes drag to be sized for the average heat load of the mission rather than the absolute peak load. This is a massive weight-saving optimization for those transient power demands.
Incredible. And finally, let's talk component standards. We've seen high-tech 3D printing, but everything, every little part, has to adhere to these rigorous aviation standards.
Oh, absolutely. The devil is in the details here, especially when you're talking about maintainability and safety. All components must be aerospace grade. For example, the fluid reservoirs are specified as a titanium alloy bellows compensator.
Okay, break that down. Why titanium and why a bellows?
Titanium is mandatory for that perfect combination of low weight and high strength. The bellows mechanism, which is basically a metal diaphragm that expands and contracts, is critical for compensating for extreme pressure changes.
At altitude.
Right. As the eVTOL climbs up to 25,000 feet, the ambient pressure drops dramatically. Without a sealed compensating reservoir, the fluid could boil, air could get ingested into the system, or the pump could cavitate, all of which lead to a cooling failure.
Which ties directly back to those DO-160G environmental requirements we saw earlier, ensuring the components are reliable at altitude.
Correct. And another seemingly small detail with huge implications: the quick disconnects. They have to be non-skill dry brake aviation grade.
And that's not just about preventing leaks.
Not at all. It's about maintaining fast turnaround time, TAT, on the ground. When a maintenance tech needs to disconnect a loop, no air can get in and no fluid can spill out. It ensures a quick, clean, and safe path back to flight. This level of meticulousness is what defines aerospace engineering.
The overriding philosophy here is that safety and regulatory compliance, what they call airworthiness, it supersedes everything else. We've talked about performance, but now we have to address what happens when this incredibly complex system fails. This is the non-negotiable safety framework.
Right. This is the architect defining the potential consequences of failure using the ARP 47601 safety assessment framework. The complexity of the P13 means that failures are classified based on the resulting impact on the aircraft.
So how serious is the loss of battery cooling, an LTL failure?
A loss of battery cooling is classified as hazardous, which means it's a major, dangerous failure condition that significantly reduces the safety margin and increases the pilot's workload.
And the mitigation strategy isn't just to fix it.
No, it's to manage the consequence. The Vehicle Control Unit, the VCU, must immediately command a power derating and force a land as soon as possible mode. The system then has to rely on the battery's immense thermal inertia, its own mass, to buy the pilot enough time for a safe, controlled landing.
Okay, what about the loss of inverter cooling, the MTL failure?
Loss of inverter cooling is classified at the highest possible level, catastrophic. If that loss leads to the total loss of critical thrust from a motor.
So a thermal failure here could mean a loss of control or total propulsion failure.
Exactly. And the mitigation demands are commensurately stringent. You have the mandatory dual redundancy in the pumps, which we discussed, and also, crucially, dedicated hardware over temperature cutoff protection.
What does that hardware cutoff protection actually imply?
It means you cannot rely solely on a line of software code to prevent a catastrophe. The physical circuit board itself must have an independent temperature sensor linked directly to a kill switch. And that switch has to function outside of the main flight control software.
So if the temperature exceeds the absolute red line,
the hardware cuts the power, even if the software is stuck in a loop or has crashed.
That reliance on hardware over software leads us directly into the software development assurance levels, or DAL. The software that governs these critical systems can't be written like a standard app.
Absolutely not. The complexity and criticality demand different assurance levels, which are guided by standards like DO-178C for software.
Yeah.
The highest level, DALA, is required for any function whose failure would be catastrophic.
Which would include?
It includes the thermal runaway detection and the automated venting control software for the battery.
And what does DALA require from a coding perspective?
It requires total absolute rigor. It demands 100% modified condition decision coverage, or MCDC.
Yeah.
In simple terms, MCDC means proving that every single logic path, every if-then-else condition in the code has been tested under every possible combination of inputs. It's the highest possible assurance level that the digital brain of the system is structurally flawless.
What kind of functions fall under the next level down, DALB?
DLE covers high safety functions. This would include the cooling system monitoring, the diagnostic software, and the fault response logic that, for instance, initiates the pump redundancy. If DLB fails, it's dangerous, but those independent DLA safety layers should still manage the ultimate consequence.
And DLC handles the non-critical efficiency factors.
Correct. DLC is applied to functions like the energy optimization algorithms and the drag management control logic. If the drag management fails, you burn more energy, but the aircraft itself remains perfectly safe.
Beyond these internal standards, the specification is built to ensure compliance with global regulators like EASA and the FAA. What's the single biggest regulatory hurdle they have to clear?
Well, EASA's SC-VTOL BAT231012, proving component temperatures are safe in all conditions, including just sitting on a scorching runway. That's critical. But the most challenging hurdle for any electric airframe is RTCA DO311A.
That's the battery fire safety mandate, isn't it?
It is. It's the mandatory requirement to prove two things. First, that a single-cell thermal runaway event, one cell catching fire, will not propagate to the cells next to it. And second, that any fire, smoke, or toxic gases that are generated have to be safely contained and then vented outside the aircraft cabin.
And there's a time limit?
Crucially, the system has to guarantee 15 minutes of containment time. That allows the pilot the critical window they need to execute an emergency landing procedure.
15 minutes of guaranteed containment of a lithium-ion fire. That is an extraordinary engineering challenge.
It is. It requires sophisticated cell packaging, often using that phase change material we talked about, and robust structural isolation with dedicated venting paths. It's the ultimate safety requirement.
And finally, the environmental envelope, RTCA DO160G.
Right. This is the standard that requires verification, that all of these components remain reliable and function between the extreme cold of -55 Celsius and the extreme heat of +70 Celsius, and all the way up to 25,000 feet of altitude. This is exactly why specifications like the titanium bellows compensator and the high breakdown voltage PAO fluid were written. They are necessary to pass DO160G.
So the entire system is built on this foundation of regulatory compliance. But theoretical compliance is meaningless without physical proof. The final phase is this rigorous, multi-layered verification and validation, or V&V, process. How do they actually prove this complex system works?
The architect designed a 3-level validation system. It's designed to expose and mitigate every possible risk long before the first flight. And it starts at level 1, the component level. This is all about durability and stress testing.
So what happens at level 1?
Well, pumps are tested for 2,000 hours of continuous operation. Components are subjected to bursting pressure tests at 3 times their maximum operating pressure to find their physical failure limits. But the most revealing test, especially for the 800-volt system, is a high-altitude partial discharge test, or PDIV.
Let's elaborate on that, on PDIV. Why is high altitude so critical for electrical insulation integrity?
It all relates to something called Paschen's law. Paschen's law dictates that the electrical breakdown strength of a gas, how much voltage it can withstand before it arcs, is actually lowest at specific low pressures, like the ones you find at 25,000 feet.
So the thinner air makes it easier for electricity to jump a gap.
In simple terms, yes. It's easier for 800 volts to arc. The PDIV test puts these 800-volt components into a vacuum chamber that simulates 25,000 feet, and then they apply 1.5 times the operating voltage. The test ensures the insulation and the PAO fluid maintain their integrity with 0 partial discharge activity. It proves it won't arc in thin air.
Okay, so if the components survive the altitude chamber, they move up to level 2, the system level, which is often called the iron bird or the thermal bench. This is where they test the whole ecosystem together.
This is where simulation gets real. The engineers use these highly sophisticated programmable electric heaters and dynamic fluid loops to simulate the exact 90-second dynamic thermal load profile of a real mission takeoff, hover, and cruise.
A dynamic thermal load simulation.
It verifies that the entire system, pumps, valves, radiators, everything, can maintain those ±3C and 150C KPIs in real time under rapidly changing stress.
And this is where they deliberately try to break the system, using fault injection testing.
Yes. They physically simulate every single point of failure they can think of. A pump motor burning out, a valve sticking in the open position, a minor fluid leak. The objective is to verify that the FDIR logic fault detection, isolation, and recovery correctly identifies the failure and shifts to the degraded safe mode.
And it has to do it fast.
Critically, the system has to trigger this recovery within 200 milliseconds.
200 milliseconds. Why such a tight window?
That's the reaction time you need to prevent a component from overheating past the point of damage. If the system takes too long to react, the temperature spikes, and a component like the 6 inverter could be permanently damaged or fail completely before the VCU even has a chance to dedurate the power.
And the final destructive test on the Ironbird.
That's the mandatory DO311A test. They intentionally trigger a single-cell thermal runaway in a battery package sample while the cooling system is running its containment protocols. This is the physical proof that the tab cooling design, the thermal barriers, and the venting system actually work to prevent propagation to adjacent cells within that critical 15-minute survival window.
So if the ground testing passes all of this rigor, it finally moves to level 3, aircraft level, flight testing. This is where you validate the real-world performance under the absolute harshest conditions.
Right. Flight testing validates the entire envelope. They do what are called heat-soaked flights. They push the aircraft to maximum power hover and climb rates in extreme ISA plus 35 degrees Celsius heat. And the engineers are monitoring thousands of thermocouples to verify that all the safety margins are maintained when the heat rejection system is at its most stressed limit.
And they also quantify the actual range benefit they get from that clever drag management system.
Through drag validation flights, they'll measure the cruising power required with the cowl flaps stuck fully open versus the power required with the flaps being actively controlled by the drag management algorithm. This gives them concrete, quantifiable data on the real efficiency gain they achieved, proving that FUNC TMS-04 actually works as advertised.
All these verification and validation stages, they lead to the final acceptance criteria, the veto points. If the system fails any of these hard lines, the entire thermal system is rejected.
These veto points, they represent the core contractual promise to the pilot. And the most crucial one is single-point failure survival. Upon the loss of any single active cooling pump, the system must guarantee a minimum of 10 minutes of emergency loiter time for a safe, controlled landing.
10 minutes.
That 10 minutes is the essential survival window that the thermal architect has to deliver. No excuses.
The second veto point, thermal control precision.
This just confirms the battery safety envelope. The battery's highest recorded temperature must remain strictly below 55 degrees Celsius after a full 5-minute hover test at ISA plus 35°C. If you exceed 55, it signals you have inadequate heat rejection capacity at peak load.
Third, insulation integrity.
The 800-volt circuits have to maintain that regulatory requirement of greater than or equal to 2 megos of resistance with 0 partial discharge at high altitude. This proves the longevity of the dielectric fluid and the insulation under real environmental stress.
Fourth, leakage rate. Simple, but critical. External leakage must be 0 cc per minute at maximum operating pressure. Aviation demands hermetic sealing.
And finally, the structural soundness of the digital brain itself.
The core thermal control logic, particularly the software that governs the automated safety and redundancy, it has to pass that 100% MCDC test verification. The architect insists that the digital control system must be just as structurally sound and redundant as the physical titanium components.
What we've seen today is not just a list of parts. It's a comprehensive deep dive into the engineering philosophy of next-generation aviation. The P-13 Integrated Thermal Management System is just a spectacular example of high-stakes aerospace engineering. It translates these incredibly complex physical challenges, the duel of fire and ice, the problem of low delta T, the sudden failure of ram air into a certified, highly redundant, and extremely efficient solution. The strategic takeaway here, really, is that thermal management has been elevated. It's gone from a supportive role to a core strategic variable. And the architect's use of that dual-fluid tri-loop MECE architecture, prioritizing the non-conductive PAO fluid for 800-volt safety, and then optimizing performance with things like tab cooling and 3D printed microchannels. It just demonstrates that holistic safety-first systems thinking is the only way forward for urban air mobility.
So if we connect this to the bigger picture, where does a specification like this point to the future? The current architecture is immensely sophisticated, but the sources do mention reserving a path for the next generation.
They do. The chief architect specifically advises future research into dielectric oil immersion cooling as the ultimate long-term solution.
Immersion cooling.
While tab cooling is the cutting edge for today's batteries, those batteries are rapidly gaining energy density. Future systems, pushing 400 watt-hours per kilogram and even higher, will generate heat so rapidly and so intensely that even direct contact cooling might not be enough to maintain that strict 45 degrees Celsius temperature ceiling.
So you're moving from just contact cooling to full submersion, where the entire battery cell is completely encased in the dielectric fluid.
It's the necessary evolution. Full immersion offers the maximum possible heat transfer surface area and the best uniformity. And that's really the only way you can maintain the necessary thermal stability and safety margins as battery power density continues its relentless climb upwards.
That brings us to our final provocative thought for you, the listener. We've seen how the current thermal management system needs to buy the pilot 10 minutes of survival time after a cooling pump fails. If the next generation of batteries gets twice as energy dense, which means they would release twice the destructive energy in a thermal runaway event, how will engineers manage that runaway risk to still guarantee that crucial 10-minute survival window without making the thermal system itself too heavy for the aircraft to even fly? The physics of containing that immense energy release is the next great challenge the architect must solve.
Food for thought indeed.
Until next time, keep those delta T's in check and keep diving deep.